So now that we know about sines and cosines in trigonometry, it's time to talk tangent. In this video, we'll get an introduction to the tangent function, the ways to think about how to understand a tangent, and then also some of the properties that the function f of x equals tangent of x enjoys. So first of all, how do I compute the values of selected tangents of certain angles? So let's think about tangent in these three different ways. On the one hand, we can think of the tangent of an angle as the ratio in a right triangle between the opposite side to that angle and the length of the adjacent side to that angle. So opposite divided by adjacent. For an angle that's between 0 degrees and 90 degrees, this works great as a definition of tangent. But for all other angles, it's necessary to think about tangent in a more expansive way. We can think of it as the slope of the line that's made with an angle of x to the positive x-axis. That slope is equal to the tangent of x. So that's another way to think about how to compute a tangent. And again, regardless of what the angle is, because the tangent is thought of as opposite divided by adjacent in a right triangle, I can divide the numerator and denominator of that by hypotenuse, opposite over hypotenuse, adjacent over hypotenuse. And what that gives me is a way of understanding the tangent in terms of the ratios that we already know. Opposite over hypotenuse is otherwise known as the sine of x, and adjacent over hypotenuse is otherwise known as the cosine of x. So the most useful and expansive definition of tangent of x is just the ratio of sine x to cosine x. So how would I use this to compute the tangent of pi over 4? Let's use the right triangle definition of tangent first of all. Pi over 4 radians is really at 45 degrees. It's 1/8 of the way around an entire revolution, right? And so a right triangle that has one of its angles equal to 45 degrees is an isosceles right triangle. 45, 45, 90 are its angles. And because it's isosceles, it means that the two sides that are opposite, the equal 45-degree angles, are congruent to one another. And because tangent is opposite over adjacent, the opposite side and the adjacent side in this triangle are going to have the same length. If I choose 1 for the length of one of them, for example, it makes the other one also equal to 1. The hypotenuse would be the square root of 2, but the hypotenuse isn't important for tangent, right? Only the opposite and the adjacent in a right triangle are what we need to know. So what is the tangent of pi over 4 according to the right triangle definition? It's the opposite over the adjacent, 1 divided by 1. The tangent of pi over 4 is 1. All right, so what's the tangent of 2 pi over 3? Let's use the slope definition. 2 pi over 3 radians is 120 degrees. So what we'd be looking at is an angle made with the positive x-axis of 120 degrees. If I draw a line that makes that angle with the positive x-axis, then the tangent of 2 pi over 3 is going to be the slope of this line. And the slope, as always, is just the ratio of rise over run, a difference in y values divided by a difference in x values. So all we need to do is locate 2 points on this line, and we'll do the usual y2 minus y1 over x2 minus x1. One of the points we can always identify on this line is the origin, so we'll just need to find one more point. I can do that by noticing that I have a 30, 60, 90 degree right triangle made right here in the second quadrant by this angle. And in any 30, 60, 90 right triangle, the length of the hypotenuse is twice the length of the smaller leg, 1 to 2. Right? And that means that the remaining side, if we use the Pythagorean theorem, stands in a ratio of the square root of 3 to the short leg. So now we have all the information we need to find some coordinates for this point. This point's in the second quadrant, and since it's a distance of 1 away from the y-axis, its x-coordinate would be -1, and its y-coordinate would be positive the square root of 3. So what's the slope of this line? It's the ratio of the rise that it takes me to get from 0, 0 to this point. That rise is positive the square root of 3, divided by the run that it takes me to get between those 2 points. And to get from this point to that point is a horizontal move of -1. So rise, positive square root of 3, run, -1. Divide those two, and I find that negative the square root of 3 is the slope of this line, and therefore it's the tangent of 2 pi over 3. Finally, what about finding the tangent of 5 pi over 6 using my definition in terms of sines and cosines? All this requires me to do is to divide the sine of 5 pi over 6 by the cosine of 5 pi over 6. And if we remember our unit circle angles, sine of 5 pi over 6 is 1/2. Cosine of 5 pi over 6 is minus the square root of 3 over 2. And so when I divide that sine by that cosine, I get the tangent of 5 pi over 6, -1 over the square root of 3. In part B, we ask a question, why is the tangent of pi over 2 not defined? Let's use the slope definition to think about why. Pi over 2 radians, after all, that's 1/4 of the way around an entire unit circle. And so pi over 2 radians is another name for 90 degrees. But what does the line that makes a 90-degree angle with the positive x-axis look like? It's this line right here. It's the y-axis. And so the tangent of pi over 2 is the slope of the y-axis. But the y-axis is a vertical line. What's the slope of a vertical line? Well, if I pick 2 points on that line and I compute the rise, I'm going to get some, non-zero number. But if I try to find the run, the difference in x-coordinates between any 2 points on a vertical line, that run is always equal to 0. So when I try to compute the slope, I'm going to be dividing 1 by 0, and dividing by 0 is the one thing that we cannot do in real number arithmetic. So the tangent of pi over 2 is not defined because the line that makes a pi over 2 radian angle with the positive x-axis is a vertical line, and vertical lines have undefined slopes. So to finish up this introduction, let's talk about the domain, the range, and also the period of the tangent function. So to do that, I'm going to graph the tangent function using a graphing app. Here I'm going to use Desmos. When I do that, here's what my graph looks like. This is the graph of f of t equals the tangent of t. Take a look first of all at where its x-intercepts are. The tangent of t is equal to 0 when t is a multiple of pi. Let's think again for a moment about why that makes sense with respect to our previous definition of how tangent works. If we think about that, remember, just behind my head here, that the tangent is the slope of the line that makes that angle with the positive x-axis. So when the tangent is equal to 0, it means that the slope of that line is equal to 0. Well, what lines have a slope of 0? Horizontal lines do. What angles do horizontal lines make with the positive x-axis? They make a 0-degree angle, a pi radian or 180-degree angle, a 360-degree or 2 pi radian angle, and so on. So that explains all of the x-intercepts for the tangent function. What about the places where my tangent function is undefined? We just decided, for example, that pi over 2 was such an example. So if I plot the vertical line x equals pi over 2, what I find out is that that vertical line looks like a vertical asymptote for the tangent function. There is no point on this graph of tangent that has an x value of pi over 2, because the tangent of pi over 2 is undefined. So, with all this information taken together, what would we say are the domain, the range, and the period of the tangent function? Well, first of all, let's do the simplest example, and that's the range. The range of the tangent function is going to be what I get if I squish this entire graph onto the y-axis. How much of the y-axis does it cover? And the answer there is that it covers the entirety of the y-axis. It's not possible for us to miss any point on the y-axis. Every value, every real number can be the value of tangent of x. And again, another way to think about that, remembering that tangent is the same as slope, I can draw a line through the origin that makes any slope that I want to, and that slope is going to be equal to the tangent of the angle that that line makes with the positive x-axis. So tangent can spit out any real number as a slope, any negative real number, any positive real number, 0, anything in between. So the range of the tangent function is all real numbers. Meanwhile, the domain of the tangent function is going to be what I would get if I squished the tangent graph not onto the y-axis, but onto the x-axis instead. If I squish this graph onto the x-axis, what am I going to cover? And more importantly, what am I going to miss? I'm going to miss exactly those points that do not have a value for tangent of t. Those are going to be the angles that I cannot find a slope for. And those are going to be the angles that make a vertical line. Right? What angles make a vertical line? Well, pi over 2 does. So pi over 2, comma 0, is a point on the x-axis that is not going to get hit by this domain. But then so is 3 pi over 2, so is 5 pi over 2, so is minus pi over 2, so is minus 3 pi over 2, so is minus 5 pi over 2. So all of those points along the x-axis are not going to be a part of the domain of the tangent function. So the domain of the tangent function is going to consist of all real numbers except for the odd integer multiples of pi over 2. So 1 pi over 2, 3 pi over 2, 5 pi over 2, negative 1 pi over 2, negative 3 pi over 2, negative 5 pi over 2, and so forth. So how do we write that using interval notation? I would recommend not getting too wrapped up in this, but one way we can write all but the odd half integer multiples of pi would be to write minus infinity to infinity, all real numbers, minus, this is how we subtract one set from another set, minus the set consisting of those odd half integer multiples of pi. Or another way, using set builder notation, would be to say that this is the set of all x's that are real numbers, such that x is not equal to 2k plus 1 pi over 2 for integers k. So if k is an integer, then 2k plus 1 is an odd integer, and so this runs over all the odd half integer multiples of pi. So don't worry too much about that notation, worry more about the idea that we can take the tangent of any angle and get a real number, with the exception of those angles that make vertical lines. And those are the ones that are the odd half integer multiples of pi over 2 angle with the positive x-axis. Finally, what is the period of y equals the tangent of x? How frequently does the tangent function repeat itself? Looking back at the graph one more time, notice that the tangent of 0, for example, is 0, but then so is the tangent of pi, and so is the tangent of 2 pi, and so forth. So is the tangent of minus pi. It seems that the tangent function repeats itself every pi units, every pi radians. Let's think for a moment about why that makes sense with our definition of tangent. So we'll say that the period of the tangent function, y equals tangent of x, is pi. It repeats itself every pi. But remember, sine and cosine don't repeat themselves every pi, they repeat themselves every 2 pi. So why does tangent do that? Why does tangent repeat itself every pi? Well, let's go back for a moment to the slope definition of tangent. If I take this line, whose angle with the positive x-axis is x, and let's say I increase that angle by pi radians, what am I doing? I'm rotating this line 180 degrees around the origin. But if I rotate it 180 degrees around the origin, that line is the same line as I started with originally. The slope is still the same. And so the tangent, therefore, of x is going to be the same as the tangent of x plus pi. But notice what happens to the sine and the cosine. Those would be the vertical and horizontal coordinates of these points on the unit circle. The sine and the cosine are both going to flip from positive to negative or vice versa if I rotate this line about the origin by 180 degrees. Therefore, the sine is going to have a minus in front of it. The cosine is going to have a minus in front of it after we do that rotation. So the sine and the cosine change, but their ratio, the tangent, does not. Because if I change the sign of the numerator and denominator of a fraction at the same time, that fraction, the ratio, our tangent, doesn't change at all. So even though sine and cosine have a period of 2 pi, tangent only has a period of pi for that reason, because the tangent is measuring the slope of the line that makes an angle of x with the positive x-axis. There's our introduction to tangent. We're going to be able to take this and do some more with it and run with it as this section goes along.